Welcome to the fourth module of 11th week. This week we have been seeing interference phenomena, and in today's lecture we will look at Young's double slit experiment. It is one of the classic experiments, and I must tell you first an important distinction between this and whatever we studied earlier. So, in all the cases that we looked at earlier, Michelson and Fabry-Perot and Newton's rings and so on, in all those cases they are a class of interference where you divide the amplitude and look for interference phenomena or interference through division of amplitude. So, what you had was you had one beam which was used to generate two beams by a process of reflection or even transmission or a combination of reflection and transmission. On the other hand, in what we are going to see today, we will actually divide a wavefront. So, there will be an incoming wavefront, and the path of the wavefront you put in a screen with maybe some slits. So, the same wavefront is now divided into two and generates for us two beams which would possibly interfere. So, Young's double slit experiment belongs to this class. So, very quick review of what we did. We looked at interference through division by amplitude. Newton's ring is a good example of that. So, in this case one beam becomes two beams through a process of reflection. So, in this case the reflection takes place from the bottom surface of this plano-convex lens and the top surface of the glass plate P, and then of course, it satisfies the usual conditions for destructive or constructive interference, and you can of course observe it. This of course is one of those observed interference pattern. And in the case of Michelson's interferometer, again what was involved was reflections at two mirrors M1 and M2. You had one source of beam and two mirrors, and the path length to these two mirrors can be varied, which provides the path difference and hence the phase difference. And again at the detector, depending on the settings, you could either see a constructive or a destructive interference. On the other hand, Fabry-Perot interferometer was the case of interference in a setup with multiple beams, because you had one incoming beam instead of just producing two which normally interfered. Now, you had many which interfered. At the top end of this Fabry-Perot interferometer, this one, it is partially reflecting and partially transmitting. So, there is a transmitted component which is finally detected, and there is a reflected component. The reflected component gets transmitted, partially transmitted later on, and so on. So, you had a large number of these beams which come out, and at some point external to the echelon, you could ask whether they would all constructively interfere or there would be the destructive interference. So, all that depends on the phase difference between the successive beams that are coming out, and depending on conditions on these, again you could work out when you will see a constructive and a destructive interference. So, the point to remember is that this is a case of many beams interfering together as opposed to two that we saw for Newton's rings and Michelson's interferometer. So, here I have two sources S1 and S2. You can take them to be point sources, and you can also assume that they are going to emit light in all directions if you like. Now, the question is the following. So, if I have these two sources S1 and S2, they are monochromatic, they are coherent sources, and they are separated by a distance d between them. Now, I take some arbitrary point P which is shown here. What would I see at P? That is the question. So, this point P is located at a distance x1 from the source S1, and it is located at a distance x2 from S2. Would I see a dark fringe or a bright fringe at P? That is a question that we need to answer, and here we are assuming that these two light sources S1 and S2 are coherent, they have the same frequency, and more importantly they will maintain a constant phase difference between them. And another piece of assumption that I need to take to make the analysis easier is that these distances x1 and x2 that I have defined here are sufficiently large enough, in the sense that the point P is sufficiently far from these two sources S1 and S2, so that when the wave fronts reach point P, you can assume that it is nearly plane waves. So, in that case I can write expression for displacement of each of these waves. So, y1 is the displacement of the wave that is reaching point P from source S1, and y2 is the displacement of the wavefront that is reaching point x2, and this comes from source S2. So, I have these two expressions, and capital A is of course the amplitude, and again for simplicity I have taken amplitude to be the same. In general they need not be, but makes analysis easier if I do so. And here calculating the phase difference is straightforward, because the equation that we have written down is already in a form where we can just take the phases of each one of them. So, the phase difference is simply the phase of the first one, which is this, is minus k x1, and phase of the second one is minus k x2. So, I just need to take the difference between the two. So, phase difference is minus k x1 minus of minus k x2. So, that gives me k into x2 minus x1, and remember k is the wave number, and we have assumed that both the sources have exactly the same frequency and same wavelength lambda, hence k will be equal to 2 pi by lambda. So, I have substituted that as well here. So, the phase difference is 2 pi by lambda into x2 minus x1. Now, what I need to see is the net effect of both these waves reaching the point P. So, just add both of them. This is a kind of problem that we had done many times over when we looked at combinations of simple harmonic oscillations. It is pretty much a similar kind of exercise. So, I have this y1 and y2. Now, I need to find the resultant, which is simply y1 plus y2, and just add both the waveforms. Now, what I am going to do is, for ease of analysis, I am going to introduce two new coordinates. My existing coordinates are x1 and x2 in some sense, and I want to introduce this capital X, which is related to x1 and x2 like this. It is simply the average of x1 and x2. And also I have already defined this delta in terms of k. So, that is another relation that I have here. So, which means that I have two relations which connect x1 and x2 in terms of some new variable capital X and delta. Now, I substitute for kx1 and kx2. I have already done that. You can see that kx1 here has been replaced in terms of x and delta, and similarly kx2 has also been replaced. And now, what I have is like sin A plus B relation. So, all I need to do is to use this standard trigonometric identity and write it in terms of product of sine and cosine. So, it turns out that in this case, if you apply this formula, so A is this omega t minus k capital X plus delta by 2, and B is this quantity omega t minus k capital X minus delta by 2. So, you do that and you will get this relation, simple application of a trigonometric identity. And now, this is of course the resultant, and now I can write what is the intensity associated with this resultant form y, which is, as we know, simply square of this quantity, and the square of this quantity is 4a square cos square delta by 2 and the usual sin square omega t function. So, we have been calling this as I0, which is what is important for the interference phenomena. This is time dependent and not quite important for our purposes immediately. So, we will look at what will happen to I0 under various conditions of path difference or phase difference. So, from here, from this formula, it is very easy to see what we should expect. So, I0 will be maximum. In fact, you will notice that I0 is a function of a cos square term. So, it is going to be an oscillatory function, and I0 will be maximum if cos delta by 2 is plus or minus 1. That is the maximum value that a cosine function can take. The maximum value a cos function can take is plus 1, minimum value it can take is minus 1, and since we are considering the square of cos function, the maximum value it can take is plus 1. And this will happen if cos delta by 2 is plus or minus 1. In either case, cos square will be plus 1, and in that case I0 will simply be equal to 4a square, and this will give us constructive interference because this is the largest intensity possible. You can't get better than this. You notice that the other term is sin square term, which also will lie between plus and minus 1. So, you can't get intensity larger than I0, which is equal to 4a square, and that will happen if delta by 2 is equal to n pi, where n is an integer. So, this tells me that x2 minus x1 should be simply an integral multiple of wavelength lambda, or in other words, the path difference should be equal to integral multiple of wavelength lambda, and this gives constructive interference. Notice that with respect to whatever we had seen earlier, in this case there are no additional phase factors that we need to consider due to reflection and so on. There are no additional contributions to the phase. So, directly if the path difference is equal to integral multiple of a wavelength, you will get constructive interference. So, I0 would be minima when cos delta by 2 is equal to 0. Of course, in that case I itself would be equal to 0. So, I0 will be 0 if cos delta by 2 is equal to 0, and this will give destructive interference, and the condition for cos delta by 2 to be equal to 0 is that delta by 2 should be equal to 2n plus 1 into pi by 2, where n is a integer. X2 minus x1, which is simply the path difference, is equal to n plus half times lambda. So, this is the condition for destructive interference, will give you 0 intensity. So, now you can ask, now that we have worked out the condition for constructive and destructive interference, now you can ask the question, what would be the pattern that I will see. So, we have this S1 and S2, which are source of monochromatic coherent source of light. They are separated by a distance d, and point P, which we are monitoring, is distant x1 from S1 and x2 from S2. The locus of points which will give us the bright or dark fringes will form a hyperbola in 2 dimensions. So, in 3 dimensions it will be this 2-dimensional hyperbola that is rotated. So, you will see patterns like this. So, there would be alternating dark and bright fringes which have the shape of a hyperbola. Let us move to the Young's slit experiment, or in this case the double slit experiment. So, here the setup is as follows. So, I have this source of light which is at the left side, and the light wavefront from this source hits this screen which has two slits, S1 and S2. To begin with, it is easier to assume that S1 and S2 would produce would be point sources of light, and S1 and S2 are separated by a distance d. And at the far end on the right side, I have this screen, and the light beam coming from S1 and S2 would of course make its contribution at any arbitrary point on this screen. Suppose I choose a point P here, which is indicated by this red dot. The question is, what would I see there? Would it be a bright fringe or a dark fringe? The distance between the double slit and the screen at the far end is capital L, and of course, S1 and S2 are separated by distance d, and from this point here, which I will call P0, to point P is a distance of z. So, P0 is the point which is precisely perpendicular to the midpoint between S1 and S2, and with respect to that line that is drawn there, the ray that is emanating from there, a notional ray, of course, there would not be any ray from there, but if I draw a line from there to point P, it will make an angle theta. This distance capital L is much larger than this distance z between P0 and P, and capital L is also much larger than this distance d between the two slits, and also I want the wavelength of light to be much smaller than the distance between the slits. These assumptions will guarantee for me that the two rays which are starting from S1 and S2 and reach point P, they are nearly parallel when they begin with, and because they are nearly parallel, we can approximately write the path difference as simply d sin theta. So, you can see that the path difference that I have drawn here is d sin theta. So, that is the path difference between the two beams that reach P from S1 and S2. You take this triangle between P0, P and the midpoint here. So, from that you can write sin theta to be z by capital L. So, once we know the path difference, straightforward to write the phase difference. So, simply substitute x2 minus x1 to be d times z by L, and I have this phase difference. And as usual, our intensity is 4a square times cos square delta by 2. So, we just need to substitute delta by 2 here and see whether we are going to get a bright fringe or a dark fringe. The fringe will be of course bright if cos delta by 2 is 1, or more correctly plus or minus 1. So, in that case the intensity would be 4a square, just like we saw the last time, and then the condition is that this would happen if this delta by 2 is equal to integral multiple of wavelength, which is given by this condition, and that is dz by L is equal to n lambda, where n is 0, plus or minus 1, plus or minus 2 and so on. So, here is my condition, dz by L is 0, plus or minus 1 and so on. So, which means that this is the condition for constructive interference. Using this, I can write this relation. So, it tells me that Zn, where n would be the nth order fringe, you will get bright fringes at Zn equal to n times lambda capital L divided by d. D is the distance between the two sources S1 and S2. Now, you can do a similar exercise for minima or destructive interference. So, the condition is dz by L is equal to plus or minus n plus half times lambda. From here I can extract the condition for destructive interference or a minima or a dark fringe. Dz by L should be equal to plus or minus lambda by 2 plus or minus 3 lambda by 2 and so on. And of course, this is a case of destructive interference, and like we did earlier on, you can now write out an expression for where I can observe a dark fringe. So, Zn, starting from this, you could write down this Zn will be observed at n plus half lambda L divided by d, n is all integers. So, you are going to see a series of dark and bright fringes. What is the distance between two bright points, two consecutive bright points, and or two consecutive dark points? So, that is simply given by Zn plus 1 minus Zn. So, just write out the expressions that we just derived, and you will notice that the difference, this is equal to lambda into L divided by d. So, the spacing between the fringes, as you can see, is a constant simply because the three factors which determine it are all constants. This also affords a way of calculating lambda, provided I know other things. I know what is capital L, because in an experiment, if you are doing it, you set up the distance between the source of radiation and the screen. So, you know what is capital L, you know the value of d, because again it is under our control. Once I know all this, I can measure the fringe width experimentally. So, if I can measure this difference experimentally, then the only unknown is lambda. So, just like we saw with the Fabry-Perot or with Michelson interferometer, the Young's double slit experiment can also be used to determine the wavelength of an unknown source of light.